morning, good afternoon. Welcome in truly across the continent for another exciting broadcast with us here at Exploring by the Seat of Your Pants. I know we've got some new faces in the crowd today, so if you're new to us, we are all about bringing conservation, adventure, and science into classrooms around the world. And you're catching us on an exciting day. Number one, it's our home stretch. We are in our final few weeks of broadcast after over 400 shows this school year alone. So much to explore and discover on our YouTube channel. Everything we do goes there. So if you want to hear from amazing scientists, explorers all over the globe, head to there. Catch this one in 3 weeks or 3 years too. Lots of opportunity to keep the learning going. And it's also exciting because we're bringing back one of my all-time favorite speakers. Now, I don't say this about everyone, I promise. We're bringing back Dr. Parshati Patel. She is an amazing... Oh, we've got cameras dropping. This is a new camera. That's the first time that's happened. That's so exciting. Sorry, technical difficulties as humor. Dr. Patel has joined us many times to share her insights and passion about the universe and the cosmos around us. Today, she's going to talk about the life and death of stars. I'm a little thrown off because that camera fell, but I'm going to turn it over to her to blow your mind and take us on a journey about the things that power life on Earth and what we see in the night sky at night. Stellar evolution and growth is one of the coolest topics on Earth, and for many of you, it'll be your first time ever hearing about this. So I hope you're as excited as I am, and we will buckle up and dive in. Parshati, welcome in.
Hello, thank you for having me. I'm so excited to be here today and talking about stars. I've always loved stars, and that's actually what brought me to astronomy and learning how, planets form. So we're going to talk a little bit about how stars form today and, what they go through in their lives and how they die. and then we'll dive into Q&A. So I'm going to start sharing my screen. There are some pictures and videos, but I'm really excited.
I'm excited. And as you're bringing this up, I want to note, if you look over her shoulder, you'll see there's this amazing book, which I also have, which was written by her. So you can get this book too. I'll highlight this at the end. If you want to follow along and learn even more when this presentation is done, it is a fantastic read. And that's my plug of the day.
Thank you, Jesse. Yes, I absolutely love that book. And the reason I wrote that book, because it's filled with pictures, which, I love looking at pictures and trying to understand what is going on. I'm a visual learner, and today we're going to do that. So when I talk about how stars form and how they evolve over their life and what happens to them when they die, it's all going to be pretty pictures. So get ready for that. We also have a video that's going to kind of take us, through a region where we do see stars forming. So let's dive into it. I'm going to share my screen. And let's, keep our fingers crossed that this is going to work.
It's going to work. It's beautiful. It's gorgeous. It would be better if it tried.
Perfect. Okay. All right. So let's start. I know I cannot see all of you, but I'm hoping that some of you have seen probably night sky like this. If you're in a classroom, please raise your hand if you have seen a night sky like this filled with stars, especially this dark patch that it's very if it's white filled with dust and lots of stars compared to the rest of the sky. This is a picture actually I took in, not so far from here, like a 5-hour drive up north. I'm based in London, Ontario. And so on this lake, I knew that there was a perfect orientation of this lovely white band that we called Milky Way. This is our home galaxy. This is where the sun and all the planets within our solar system and us live. And it's an amazing opportunity during this time up until, late August, early September. You can actually see the core of the Milky Way. That's what you're seeing right here. But what's really interesting is that all the dots you're seeing are stars. Okay, these are so many stars. When you do go out of the city and see these, it blows your mind. And what's really interesting is that you see stars of different colors. Okay, some of them are red, some are blue, some are just pale white. And what I love about, looking at these stars is I always wonder, what are these stars? Are they like our sun? What phase they are going through? Are they going to die soon? What's happening with these stars? And so let's look at, let's first think about how many stars there are in our own galaxy. So if we think about where the sun lives, including our sun, get ready for a mind-blowing number, 100 billion, okay? It's a huge number. I cannot myself fathom how many stars that is, okay? And that's just in our Milky Way. And then we know that there are trillions of galaxies, billions of galaxies out there. And like if you combine all of that, like it's a mind-blowing number of how many stars that are in the universe. And so that's really exciting because now we have latest technologies to actually go and photograph these things. The way we learn about the universe is actually taking pictures. Just like a picture I took here, we take pictures of, various aspects of the skies. You're looking at stars, you're looking at where they're forming, different kinds of stars, and we're going to look at some of those pictures today. So here is a picture of what we call a stellar nursery. So this is a region where you have everything that a star needs to form. So you have dust, you have gas, you have a lot of like winds flowing around that are, getting all these dust and gas to like smash into each other. This particular picture is actually of my favorite region, the Orion Nebula. So if you have looked up in the sky, there's the Orion constellation. Generally, wintertime, you can see it. Right in that constellation is this nebula. So we also call it stellar nurseries, star-forming regions. There are lots of different names, but they all mean the same thing. This is where the stars form. Okay, what I love about this particular image is that there's so much variety. If you look at, there's this blue star here. There are lots of small stars here, and you see lots and lots of gas and dust. Okay, and this is really what a star needs. It needs this particular kind of area where you have a lot of dust that it can bring together to make a star. Okay, and what's really interesting is that we have had telescopes that are looking at these regions for a very long time. And so when you're able to, look at these regions and take pictures, you can go a little bit further down and see what these stars are doing. And because I love to understand how these stars are forming, we look at what we call proploids. So this is a shorter name for protoplanetary disks. So when you have a star that is forming, you have a clump of, dust and gas that's trying to like stick together. Slowly it becomes a little bit bigger, just like, how a snowball kind of rolling off the hill, it's a little bit smaller. As it rolls off, it becomes bigger and bigger. Here in a star forming region, you have a little bit of clumps that are just gathering a lot more dust and gas. And as they get bigger and bigger, gravity takes over. Okay, and that's when you start getting something like this. So this is the same picture that I showed you before, but now zooming in to these stars that are just forming. Okay, and you can see that they're all different kinds. The first one on the top right here, it's just a small disk with a really bright star in the center. But then you have some that seem to have a bright star and then dust blowing off of it. Okay, and they all come in different shapes and sizes in terms of, what's around the star. And in this particular phase, when they're still trying to form, we call them protostars. So protoplanetary disks is material around these stars, and a shorter version of that is proploids. we astronomers like to put, very literal names and then give acronyms to it or shorten names to it. So we call them proploids. And what I absolutely love about this picture is that it shows us variety. And Hubble, one of the very famous space telescopes, took these pictures and then we made a mosaic. I was like, oh, how many different kinds are there out there? And this is on the left side you're seeing is all these different kinds of protoplanetary disks or these protostars that are forming with material around them. And you have dust and winds that are blowing in the region. And so you have these sometimes tails, sometimes you see this material flowing off of the star. It's very, very interesting. What I'm going to do next is I'm going to show you, imagine if we had a spaceship and we were to hop onto it and we were able to fly through this region, this particular region that I just showed you a picture of, how would that look? So let's go and try and hopefully this works. And it is working. So what we're seeing is if we were in a spaceship, we were to dive, we have so much information about these areas that we can actually create a 3D version of how it would look like if we were to dive through this nebula. And as you can see, there are lots of different stars. There's a lot of gas and dust around us. And they're in different sizes too, right? There's some really big, some really small. They actually use two different kinds of telescopes to come up with this particular I want to go back and show you that pretty interesting you can see right here a really nice protostar that has, wind blowing around it. It got me distracted, but it's really interesting. And what I love about this particular animation is it shows us how it would look like, how it's 3D. Even though our pictures show us something that's like in the sky, seems like 2D feature, but when we actually dive into it, it is a giant cloud of dust and gas with stars actually forming. And we scientists get to actually study these, and we are able to take pictures. We're able to take, the amount of light that is sending us, and we utilize all of that to actually figure out, what is happening with these stars. So if we are able to take lots of pictures of these stars, which we have been able to do, we can actually put them in bins and bin out, okay, which star is at what phase in its life. If there are two stars that are very similar, you can put them together, be like, okay, they seem to be very similar to each other. And that's how we figure out what is happening with these stars. So let's look at the life cycle of a star. So from birth to what it does throughout its life, and then when it dies. So for a sun-like star, this picture is going to be a little bit confusing, but we'll go through it the entire thing. So let's start in the star-forming nebula or star-forming regions, as I just showed you a picture of, which is right in the center of this image. And if it was a sun-like star, so it's not too big, not too small, what will happen is from that protostar stage, it will take quite some time to get to what our sun looks like right now. So our sun is in what we call a very stable, probably the longest, it is the longest phase of its life, called the main sequence phase. This is where you have, it's made of hydrogen and helium, a lot of hydrogen, a little bit of helium. And what happens in the center is that it's so hot that you have these two hydrogens smashing into each other. They're slamming into each other, and they create light, heat, and more helium. So they keep adding that, and it takes billions of years to get to its next stage. So our sun is just halfway through its life, okay? Just halfway through. So we still have around 5 more billion years before it's going to go to what we call the next stage, the red giant phase, okay? Up until then, we're good. We have 5 billion years to figure out what we're going to do next with Earth, because when the fuel, which is the hydrogen at the center of the star, is exhausted, you're now left with all of this helium. But to be able to burn that, you need a lot more temperature than what it is right now. So the center of our sun right now, it's around 15 million degrees Celsius. So on the surface, it's around 6,000. So it's very, very, very hot, way hotter than anything you can find in our house, okay? Our ovens are like 400 degrees, like very, very much, very, very cool compared to what we deal with when we talk about stars. And so when it does get to this red giant phase, and it's filled with all the helium, it's trying to burn that helium, needs, a lot of temperature. And before it gets to that, it actually collapses on itself and shrinks. And in the same time, it gets heated up, because it's shrinking, it gets hot right in there. And what happens is you have the star, because now it shrank and it got hotter, it now starts to expand a bit. So the red giant phase is really, it's giant because it starts to expand, okay? And when it does get to that temperature, you do have, the helium in the center starting to burn, okay? And then it does that for a while before it runs out of helium. And when you do not have a very high temperature, you cannot do anything anymore, okay? So what it does is it goes to the next phase of its life, is what we call planetary nebula. So while trying to burn helium, it's shedding all of these, layers around it, which you see in form of this nebula. It is not like the nebula that we saw before, not like the Orion Nebula. This is not where the stars form. It's just a very strange name astronomers gave. For it doesn't make planets. What it's left with is a star in the center and layers of the star's material going outward. Okay, that's why it looks like there is something in the center here and it's going out. Okay, and I'll show you a beautiful picture of, we have taken with telescopes. This is just a graphic that was made to understand what happens to sun-like stars. And what is interesting is that when these layers are expanding out, what you're left in the center is what we call the white dwarf star. So this star, it doesn't have the energy anymore to do anything for the rest of its life. It's just going to chill and cool down. That's all. That's all it's going to do for the rest of its life, okay? And for sun-like stars, they take a very long time to go through this cycle, okay? For massive stars, so stars that are 8, 10 times bigger than our sun, they go through their life really fast, okay? They go through similar stages. So they're born in a star-forming region. They go through the main sequence phase that I talked about, where they burn the hydrogen right in the center and create the helium, but they're more massive, they're bigger. Okay, way bigger in size compared to our sun. What's really interesting is when they get to the red giant phase, when they have exhausted all the hydrogen and they're now, just left with the helium. They were already big compared to our sun, when they were in their main phase of the life, main sequence phase of their life. So then instead of red giant, you get red supergiant. So you get these stars that are way bigger. These are the biggest stars in the universe, okay? Those are red supergiant stars. And what's really interesting is that when you have these kinds of stars, you can actually generate the amount of heat to burn that helium into something else, carbon into oxygen. There's a whole row of elements that, are actually within our body. For example, the iron. You get to that point, and then it's do not have the energy anymore to actually smash two atoms in together to create something new. Instead, when it gets to, something like iron, it sucks energy out of its environment, okay? And this is when you get a supernova, which are super cool. They're really bright objects. They shine very brightly, almost, to the brightness of its galaxy, even outshines that sometimes. And then you end up with one of the two, what we call stellar remnants, or what is left over of this explosion. So depending on the size of that star, you could either have a neutron star, and I'll show you a picture of a black hole, which, a couple of them are really interesting. And a lot of people asking, what are black holes? And so they're leftovers. For sun-like star, you get a white dwarf. You do not get a supernova, but if they're really massive, you get a neutron star. So just to kind of highlight, let's ignore all the numbers in there, but let's look at, what our sun-like star would have. It will have, it will die as a white dwarf. And for stars that are way more massive, they'll go supernova. And then you'll end with what we call a neutron star. So these are very, 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 very tightly packed stars. So they could be the size of our city, so maybe 20 kilometers in size, but they could pack as much material, even way more than what our sun has. So they're very, very dense. If you take a teaspoon of that, oh my God, it's really, 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 really heavy material, okay? Packed in a very, very, very small size. And then you have black holes, which are super interesting because they are so tightly packed. They have material so tightly packed that even light cannot escape it. Because imagine this, we're seeing these stars because the lights are coming from them to us to be able for us to see it, okay? But if nothing is coming from the star, from the leftover, which is the black hole, how do we even see it, okay? And I'll show you a picture that we took, the first picture of a black hole in 2019, not too far, okay? 2019. And we were able to take a picture and it confirmed what we thought a black hole would look like, where you do not have a light coming back to us. And so what we're seeing is material around it. But let's look at some pretty pictures of these, phases that we talked about. So first up is planetary nebula. Look at these. These are actual images of planetary nebulas that we have taken. Remember, planetary nebula is what sun-like stars will go through. Our sun will go through, in quite a lot of time. Not right now. We have billions of years before that happens. It will first go to the red giant phase in 5 billion years, and then slowly it will chart towards becoming something like this. So on the left side, we have the Butterfly Nebula, okay? So this particular picture was taken through Hubble. You can see a lot of material coming off of it. We are looking at it from the side. So it looks like, there are two jets coming off from the star, which is right here in the center. And then on the right side, we have what we call Cat Eye Nebula. We love naming things very interestingly. And so this particular nebula was actually the first one ever discovered. And it's beautiful. You can see the white dwarf, the leftover star right in the middle. And then you have all of these layers that the star has shed it. And we are able to take really great pictures of this. And I did not want to add any James Webb telescope pictures because I know there's a presentation coming up right after me that is going to talk about James Webb. But that's the newest telescope, and that has taken even more amazing pictures of these kinds of objects in the universe. So, but these are Hubble pictures. Hubble is like the telescope a lot of astronomers up until now, up until the James Webb came around, were using to study the universe. Next up is supernova remnants. So we don't have pictures of supernova, like right in action. We have some images where we can see a supernova like going off. It's brightening up the galaxy, and then it dims down. But these pictures, again, super beautiful, are of the remnants of what happened, like what's left over after a supernova. So you can see it's like it blasted the material out. On the left side, we have what we call Cassiopeia A. It's a remnant of a massive stars that exploded around 300 years ago. So not too long ago, but you can see how beautiful it looks. All of this is like hot gas that is being, blown up and across the universe. And then on the right side, we have the Crab Nebula. This is also a remnant of a supernova explosion. And this is actually the one that has been recorded for a very, very long time. And I'm not saying like last century or anything. More than 1,000 years ago, people noted this particular nebula, particular supernova going off. So, and this is one of probably the most well-studied remnants that we have had. And last but not the least, I will show you the picture of a black hole that we took using the Event Horizon Telescope in 2019. So there are much better versions of this now, but this was the first image that we took. And as you can see, the center is dark. This is where the light isn't coming from. But then surrounding the black hole, there was a lot of material that gets heated up as it's being dropped into this black hole, and that's what we're seeing, and that's actually how we try and infer whether or not black holes are there, is by looking at the surroundings of a black hole and what it's doing. So I'm right at 20 minutes, so I'll stop right here and we'll take questions and we'll see, what kinds of questions you have. Stars are my absolute favorite, and I'm hoping that they're now your favorites too.
They are certainly pretty cool, or pretty hot, as it were. We don't want to. They're not cool. They're boiling, way hotter than an oven, as we discussed earlier in the presentation. You're out of the presentation. That's fantastic. We've got a bevy of questions on our YouTube channel already. Madame Karine, Fairview Elementary, we're going to come to you for questions live in a minute. We're going to start with some of our online ones to let our live classes percolate. So, are there ovens that can simulate a sun? We talked about this related to what's online. Is there anything that we can do on Earth that comes close to the heat of a star?
Not really. The center of a star is millions of degrees. Like, that is very hard to do in real life. What we do as astronomers is actually recreate these stars in our computers. We create simulations because we understand the physics. We know how things are behaving and moving. We can actually predict a lot of where what goes through in a star while it's evolving. We actually use these computer simulations to actually figure out what is happening and try and then match it to what we are observing. That's actually what I did for my PhD. Is I studied massive stars and how they form with all of these disks around them. And I created them in my computer because I understand what is happening at certain temperatures, and then try and match it to if what I'm seeing in the sky from light is the same thing.
Very cool. Thank you for the detailed answer, and congrats again on your PhD. I was saying to our classes live before we got underway that I was in this cohort of great science communicators, and every other one got a doctorate except for me. So I get to call them all doctor, and they get to be like, "Hey, you," which is pretty fun every time I get the chance to have them on.
You have an honorary doctorate.
Thank you. Oh, cool. As bestowed via YouTube. Madame Karine at Col St. Charles, if you guys want to come on in Quebec, unmute your mic and you're good to go. Hey.
There we go.
Hello. I have to ask you a very important question. Do you work for NASA by any chance?
I don't work for NASA. Most of the scientists actually work at a university in research, at places where research happens. A lot of people do work in NASA too, in US, but I'm based in Canada. I have in the past been on assignment to the Canadian Space Agency, and actually our next speaker, Natalie, she is the outreach scientist for the James Webb Telescope and has worked with the Canadian Space Agency as well. So, in Canada, most of the scientists are working at universities, and, they do collaborate with researchers at NASA and at CSA and other places around the world as well.
I'm really glad we brought this up because I know when I was a kid, if I thought space, I thought NASA. Like NASA does have tons and tons of scientists, engineers, astronomers, etc. And we've had a lot of NASA programs, but in Canada, we have our own space agency. Europe has its own space agency, Japan, increasingly internationally. It is the golden age of space exploration. And so basically, when you have people come on from various countries, they're probably related to that space agency in some way or other. And as you mentioned, universities are where you'll find most astronomers. I'm in rural Western Newfoundland, and we have astronomers that work here at our campus in a town of 20,000 people that aren't with NASA, they aren't with the Canadian Space Agency. They're independent of both. So cool question, man. Thanks for that. Fairview Elementary, I will head to you guys in just a second. I'm going to take one more from you two before we head to Wisconsin. Miss Jack's class wants to know, will the sun become a white dwarf?
Yeah, so our sun will eventually become a white dwarf. Obviously, it's going to take a long time, like I said before. So it's not going to happen like soon. It will take at least 5 billion years for it to get to the red giant phase, and then millions of years before it starts shedding out its material, and then eventually it will become a white dwarf and just chill in the surroundings. One thing I will say, if we are still here on Earth by that time in 5 billion years, because in the red giant phase, they start to swell up, we may have to find a new place to live. So, all of the folks who are wanting to be planetary scientists, it's time for us to start finding an exoplanet we could move to.
And that's a long way away. I want to stress to our younger kids, we are longer than the Earth has been around, which is a very, very, very inconceivably long time before we have to worry about that. But it is something that if we, again, as you said, if we're around in 5 billion years and we're like maybe floating brains at that point, we may need to migrate further out into the solar system to survive. Yeah. Fairview Elementary, Pulaski, I want to head to you guys. If you have any questions for Dr. Patel, welcome in, third graders, and take us away.
Go ahead, Grant.
How big are black holes?
That's a great question. So it really depends on, so there are actually two kinds of black holes at the center of our galaxy. So that picture that I showed you right at the core of our Milky Way galaxy, there is what we call supermassive black holes, and they are humongous. It's even hard to fathom how big they are. Then there's another kind of black holes that are stellar mass black holes. There's the one that I talked about where you have massive stars that end up becoming black holes, and those can be, what's really interesting about black holes is they fit a lot of material in a very small space. So, if something like 10 to 20 times the mass of our sun were to become a black hole, it could be size of our sun. So, but it's a black hole. Our sun is not going to be a black hole, so don't worry about that. But they could be really small, but you could also have supermassive ones that actually exist at the center of every galaxy that we know.
And I want to harp on something here because I think it's very, very important for kids to know. If the sun were replaced by an exact same size black hole right now, I know you wouldn't be getting light from it, so that would be a bummer in a lot of ways, but it's not like it would suddenly suck us right into it. That's not how they work. It sounds really counterintuitive based on what everyone thinks, but I'm glad you're nodding and I've got this right too. That makes me happy.
Yeah, that's very right. And it's important to think about how important our sun is right now. Like from what you said, if we were to have a black hole, we do not have light. So, if you're thinking about the life we have here on Earth and why we need the heat, and we definitely need that in order to survive and have water and all of that. That's like why it's good that we are like right in the right phase of the sun, which is the most stable and the longest one, where we have a good source of heat and light that we need to be able to survive.
Amazing. Well, thank you for that deep dive into black holes. Madame Karine, I'm going to head back to you if you have a second question. No rush, everybody. I promise it's okay. But come on in, unmute, and we'll be good to go. Welcome in. Hello.
Yeah, we're back. Okay,
You're back.
I have another story then.
With a great chair.
Yeah, here we go.
Do you have like how you showed us like the pictures of the nebula, like the simulation thing of the nebula if you're on a plane? Do you have one for like a black hole or something else?
I currently don't on my computer, but we do have a lot of simulations of black holes that a lot of scientists who do study black holes have created, and they can be found on lots of different like NASA websites, but also other websites where they have used, especially the Event Horizon Telescope. Their own website also has lots of animation of what it could look like. What's really interesting is that a lot of those animations have actually also been used in sci-fi movies. So, I'm not going to name any of the movies, but it is popular enough that these simulations are accurate enough that we're able to predict how, a picture of black hole is going to look like. But they're also really fascinating that a lot of people actually use them in lots of different sci-fi movies to show what a black hole would look like if we were to travel to one.
My favorite is Cosmos, which is just one of the best documentary series of all time. Cosmos does such an amazing job of highlighting black holes, cutting edge visualization in the last few years. So, in fact, it's probably more than the last few years now. I feel like I'm getting older just thinking about when Cosmos came out. I'm not even going to look it up. I don't want to know. We're going to steer it a little back away towards more stars before we head back to Fairview Elementary. Let's see. Can a star be tracked based on temperature, or do they react the same way based on specific temperatures? So can we learn about stars and what they're like based on temperature alone?
So the interesting thing is that we astronomers like to bin things in. Like I said, when I was talking about when we look at these stars, we look at them for different characteristics, like how big are they, how massive they are, what's their surface temperature, which phase of their life they're in. So we do like to bin those, and temperature is one of the things that we actually to study. And what's really interesting is that the colors that we see actually correspond to the temperature on the surface. So for example, if you see whitish blue star, that's a really, really hot, massive star. Compared to, something like that's really, really small compared to our sun, you would see there like a little bit of reddish color. So we do look at the stars with the help of like temperature. And what's interesting is that because we know the color, because we know how big they are, based on that, we can predict like what the temperature or average temperature would be on the surface. We can say whether the star is big or small. And then based on that, we know from the life cycle that I showed you that, if they were a really massive star, they will follow that massive star cycle, versus if it was something like our sun, then it would follow that other cycle that I showed you. So we can say a lot by just knowing the color and the temperature of a star.
Very cool. And I want to stress again, we go more into that in my book of stars and planets if you want to check it out after. It's a very cool book, honestly. Fairview Elementary. We're going to head back to Wisconsin. Time flies and you're having fun, folks. So we are nearing the end of the broadcast. We're going to take a few more questions before we wrap up. Pulaski, come on in, guys, and take us away. Hey.
Why was the black hole have orange outline on the edge?
That's a great question. So the reason why it had the orange is because that's the material that is being heated before it actually falls into the black hole. And so we astronomers predicted that this would happen because that's how we detect a black hole, like what is happening around it. Because we cannot see the black hole itself, we look at what the stars are doing around it. So if you had, stars that are going around something, but we cannot really see what's happening in the center, we try and, point our telescopes to it. And when we do, we see that the material that's about to fall into the black hole is getting heated up. because it's being, turned around the black hole. And that's what we are seeing is the orange part is the heat in the material that's around the black hole. And if you were to look at simulations of these, you can see that that's always the case. You always have material around the black hole, and that's what it looks like. And we're hoping we have a lot more better pictures than what I showed you, and hopefully we'll have better pictures as we go through, the more James Webb and like other different kinds of telescopes that we will be using in the future to look at black holes.
The fact that we can see it at all is amazing. And kids, you guys are growing up in an era where you don't have the context for this. But I mean, for Dr. Patel, who's literally in this field, like the fact that we've seen gravity waves and we've seen black holes, and we found the Higgs boson, like all these things that we've been thinking about and conceiving of for decades or centuries. And then it's in the last 2 years that we've had these incredible breakthroughs. So it's a really exciting time to be an astronomer or astrophysicist because there's so much more to explore and discover. And I'm so glad we got that question. Kudos to you guys.
Can I add one thing? I know this is going to date I'm going to date myself, but when I was, I saw a grade 3 class when I was your age. I'll not mention the year, but it was early 90s when we first discovered an exoplanet. So these are planets outside our solar system. And now we have like thousands of exoplanets that we know. So even like in that short amount of time, we have discovered so much. And this is like a peak time for us. If you want, this is one of what you want to pursue. We have lots of technologies, newer technologies that are coming into picture that help us expedite what we're learning on such a massive scale compared to what we did in 50s, 60s or 70s.
It's the best time to be ever interested in space, whether you want to explore it literally, like physically or virtually or through robotics. It's just the coolest in every way. I also, speaking of dating, I looked up Cosmos 2014. So a decade ago, Cosmos came out, which is terrifying. Madame Kareem, we're going to wrap up with one more from you. Classes, do check out our YouTube channel for more with Dr. Patel. If you want to catch us with Natalie right after on James Webb Space Telescope, there's so much to explore and discover there. But we're going to wrap up in Quebec. Come on in and take us away, folks. Hey.
Hi, my name is Jace. What was your favorite subject to study in elementary or high school?
Ooh. Thank you for that question. I was a curious kid just in general, in terms of I remember having books on history, geography. I remember having this thick story. I grew up way before internet. So it was all about books for me. And I used to have this thick book of the map of the entire world. And so every city and town, I was curious about everything. But I think if I were to pick one subject, I think physics in high school was my favorite. Even though I did not really do well on physics in high school, I always thought it was fascinating how you could interpret a lot of those things. You can understand nature around you by just putting these things into formulas. And, again, like I said, I was not good at it, but I loved learning about that. And I think that's probably also why I decided to do astrophysics, was because I was oh, this is fascinating. Now I just want to take this and apply to the stars and the planets and the universe. But yeah, physics was my favorite in high school.
I figured as much, but I want to stress that it's really interesting when we have these broadcasts. We have a lot of people that do end up doing something that was their favorite thing in high school, and we have an equal number of people that found their career path when they were 25 or 28, long after they were done university or didn't do university, what have you. So there's so many routes to do something that you're truly passionate about. Some people, I knew what I wanted to do when I was 4. I love science communication. I love to talk about this and help share stories. And I'm really lucky to get to do that. But if you don't have something that really sparks you right now, keep finding new things and you'd be amazed at the thing you'll find that really gets you up out of bed in the morning.
And I'll add one more thing to what you just said is your passions can change. So, I always loved astronomy and that's what I did. And while I was pursuing my PhD, I learned about science communication and that became my passion. So, be open to different things that make you curious and things that make you happy. And you create, you become something different because you're changing, you're learning new things, you're experiencing new things, and your perspective changes, and be okay with it. So if you are planning to go do something in university and then you're now I found this that's really interesting, doesn't matter what age you are, go for what you're passionate about now.
There is no better message than that to wrap up our broadcast. YouTubers, if you want to scream and yell at home, please do. Madame Karine, Fairview Elementary, thank you so much for joining us. Quebec, Wisconsin, all over North America today. I'm going to bring you in as classes to say thank you and goodbye. And if you want to check out Natalie's program, it's right after this on our YouTube channel. Please do catch it. It's a nice double feature. But Madame Karine, Fairview, thank you so much. You two have a wonderful day. Bye.